Magnetism and Its Uses by Anne Campbell. Magnetic fields. The objects shown on these 2 pages are made from different materials. They work in different ways, but each one is either a magnet or has a magnet inside. Magnets attract iron, steel, and some other metals through their magnetism. Magnetism is the force that acts on moving electric charges and on magnetic materials that are near a magnet. The moving electric charge in fans and flashlights produce magnetism. The magnets that we use every day, such as the refrigerator magnets that we use to post things, are usually pretty small. They contain a small amount of magnetism. But other magnets, such as the ones that keep maglev trains running, are much larger. Maglev stands for magnetic levitation. The magnetic forces created by the electrical current running through the maglev train tracks lift the entire train off the tracks. Magnets create pushing and pulling forces to move the train along the track. Magnetism makes the compass needle left point in a different direction. It makes a maglev train below run. How magnetic fields work. A magnet's magnetic field can cause objects to move closer to or farther away without actually touching the magnet. A magnetic field is the space around a magnet in which magnets force operate. A magnet's magnetic field surrounds it in all directions. You cannot see a magnetic field, but you can use iron fillings to outline it. If you place iron fillings around a bar magnet, they will line up to recreate the magnetic field. They show the lines of force that surround a magnet. A magnet poles. Notice the fillings in the pictures are gathered near the ends of the magnet. They have been attracted to the magnet's magnetic poles. Magnetic poles are 2 ends of the magnet. One pole always points north, while the other pole always points south. A magnetic field is the strongest at magnet's pole. Iron fillings show this bar's magnetic field. Different magnets' magnetic fields. Look at the picture at the bottom of the page. It shows a horseshoe magnet. Its shape is totally different from the shape of the bar magnet on page 4. It is also shaped differently from donut-shaped magnets. Magnets' different shapes cause their magnetic field to be shaped differently. But there are patterns to all magnets' magnetic fields, and each magnet's magnetic field has curved lines of force spreading out from each pole. The lines run from pole to pole. At each magnet's pole, the lines of force are closest together and the magnetic field is strongest. Compare the horseshoe magnet's magnetic field with that of the bar magnet. The behavior of magnetic fields. A magnet's like and unlike poles are similar to like and unlike electric charges in the rules they follow. Just as unlike electric charges attract, so do unlike magnetic poles. And like magnetic poles repel, just as like electric charges do. The pictures show 2 magnets that are repelling each other. The magnet's north poles are trying to push away from each other. But what would happen if one magnet's north pole were placed next to other magnet's south pole? The magnets would try to pull together. You can scatter iron fillings around the magnets that are attracted and repelling each other. The fillings will show how magnetic fields change shape based on attraction and repulsion. Attraction pulls iron fillings together above. Repulsion pushes them apart below. What happens with broken magnets? Suppose you took 2 magnets and broke it in 2. What would you think would happen? If you predicted that there would be 2 new magnets, you are right. But there is more to it. Each new magnet would have a north pole and a south pole. You cannot have a magnet with only one pole. This must have an opposite pole. So magnetic poles always come in pairs. Pieces of a broken magnet may look different, but they still work like other magnets. Magnetic effects. Compass needles are a type of magnet. A compass needle always swings so that one end of points north and the other points south. Many ancient sailors used compasses to navigate. When Christopher Columbus crossed the Atlantic Ocean over 500 years ago, he used a compass. William Gilbert, working about 400 years ago, proposed that the Earth was like a magnet. He believed that it was surrounded by a huge magnetic field. Today, scientists believe Gilbert was right. But how can they be sure? They cannot, since they cannot see inside Earth. But they suspect that Earth's outer core is made up of very hot iron, liquid iron. Earth's rotation causes electric currents to flow in the iron. This creates a magnetic field. Earth's magnetic field and related features. Magnetic North Pole, axis, South Pole, magnetic South Pole. Magnetic minerals and poles. For thousands of years, people have noticed that certain rocks and minerals have magnetic properties. Magnetite, also known as lodestone, is highly magnetic. Sailors would use lodestone as a kind of early compass. Magnets have magnetic poles. Earth's magnetic poles are different from its magnetic minerals and poles. For thousands of years, people have noticed that certain rocks and minerals have magnetic properties. Magnetite, also known as lodestone, is highly magnetic. Sailors would use lodestone as a kind of early compass. Magnets have magnetic poles. Earth's magnetic poles are different from its geographic poles. The geographic poles are on Earth's axis, the invisible line around which Earth spins. But the North Magnetic Pole is almost 1,000 kilometers from the geographic North Pole in Canada. The South Magnetic Pole is found in the ocean near Antarctica. Magnetite's magnetic field pulls iron filings toward it. How compasses work. A compass's needle is magnetized. It is set within the compass so that it can turn in a complete circle. No matter where you travel with a compass, one end of the needle will always point towards Earth's North Magnetic Pole. But why does the compass needle do this? It is attracted to Earth's magnetic field. Look at the picture on pages 8 and 9. Our planet's magnetic field is shown by lines that run north and south between the magnetic poles. The compass needle lines up with Earth's magnetic field. As you know, magnetite is highly magnetic. It is so magnetic that it can affect a compass needle. What happens if you walk by a piece of magnetite while holding a compass? The magnetite's magnetic field causes the compass needle to swing towards it. After you walk past the magnetite, the needle will swing back towards the North Magnetic Pole. Compass needles swing away from the poles if a magnet is placed near them. Studying Earth's magnetic field. Compasses are good at showing us Earth's magnetic field. But any magnet, not just a compass, can be used to detect it. Take a simple magnet and tie it to a string. Then hold the string in your hand so that the magnet hangs in the air. After a few seconds, the magnet's pole will swing so that the North Pole is pointing north and the South Pole is pointing south. You can check your hanging magnet against a compass to find out which pole it is. Place the compass far enough away from the magnet so they do not affect each other. The magnet's North Pole points the same way as the North Pole of the compass needle. You can then label the poles of your hanging magnet. Making your own compass. All you need to make your own compass are a few simple objects. First, find a needle, bowl of water, piece of cork or sponge, and magnet. Then rub the needle on the magnet. Make sure that you rub it quickly and in the same direction every time. This gives the needle a magnetic field. Next, place the needle on the cork or sponge. Put the cork or sponge in the bowl of water with the needle. Make sure the needle is floating above the water and that the water is still. The needle, like a compass, will point north and south when it lines up with Earth's magnetic field. Like with your hanging magnet, place a regular compass a safe distance away from the needle. Then you can figure out which end of the needle is the North Pole and which is the South Pole. Rubbing a needle on a magnet will give the needle a magnetic field. Using your compass. Your compass needle is now made, but you will still have to mark the bowl of water as if it were a compass. Write north, south, east, and west on the edges of the bowl. Make sure the words are equally spaced around the bowl. Then turn the bowl until the needle is pointing at where you wrote north. You now have a working compass. Your new compass would be difficult to use in the woods, but it works just the same as a regular one. Homemade compasses work like all other compasses. Their needles are attracted to nearby magnets. North, east, south, west. Electric currents and magnetic fields. Hans Christian Ørsted was a Danish scientist. In 1820, while running electric currents through a wire, he saw something interesting. Each time he turned on the current, the needle on a nearby compass moved. What Ørsted had discovered was that a magnetic field is made by flowing electric currents. Ørsted had demonstrated the relationship between magnetism and electricity. Hans Christian Ørsted. Michael Faraday was a British scientist who built on Ørsted's work. In 1831, he saw that electric current could be made by moving a magnet inside a wire coil. Faraday had invented the dynamo, a device which makes electricity by using a moving magnet. You can see how a magnet makes electricity by watching a meter that measures electric current. The meter needs to be attached to a magnet that is inside a coil. If the magnet is not moved across the coil, electric current will not flow. The meter will read 0. Suppose the magnet is moved back and forth across the coil. Energy will flow through the wire to the attached meter. The needle on the meter will move past 0. Michael Faraday. What is an electromagnet? Each coil of wire with a dynamo makes up an electromagnet. An electromagnet is a coil of wire with many loops through which an electric current passes. As the current flows through an electromagnet, it creates a magnetic field. If you place a magnetic bar inside of the coil of the wire, the electromagnet's magnetic field will become stronger. You can also add more coils or wrap the coils closer to each other. Each of these changes will make the electromagnet's magnetic field stronger. You can strengthen the electric current that runs through it. This can be done by using more batteries. A stronger electric current will make a stronger magnetic field. The magnetic resonance imaging (MRI) machine uses magnetic fields to make images of the human body. Electromagnets all around us. We use electromagnets every day without realizing it. For example, every time you turn on a computer, you are using an electromagnet. Its electromagnetic is very different from the kind you just read about. Computers' electromagnets are found inside of the computer's hard drives. The electromagnet that you read about on page 16 is the simplest kind. Today there are many more types of electromagnets. They are different sizes and shapes. They have different purposes, but electromagnets work only when an electric current flows through them. Then they create their magnetic field. Laptop computers contain hard drives that use electromagnets. Electromagnets in machines that make sound. The speakers for a sound system use electromagnets. These electromagnets create changing magnetic fields. The magnetic fields change as the current changes. The changes to the current cause motion in the speakers. This motion, also known as vibrations, make the sound waves you hear. Speakers use electromagnets to create magnetic fields. These fields help create the sound waves that you hear. Earphones are other kind of sound system. Each set of earphones contain a metal disc. This disc is located in the front of an electromagnet. As with the speakers, the magnetic field of the earphones changes as the electric current flowing through them changes. The changes in the earphone magnetism causes the metal disc to vibrate. The vibration causes the sound waves that you listen to. Earphones and speakers work in much the same way. Both use electromagnets. Electrical energy into mechanical energy. Along with speaker systems and earphones, we use many devices that spin. These devices use motors to change electrical energy into mechanical energy. The energy involved in motion is mechanical energy. A rotor is found at the center of a simple motor. A battery inside of the motor creates an electric current. The electric current makes a magnetic field in the rotor. The two poles on the rotor's magnetic field repel and attract the poles of the magnets that are inside the motor. This makes the rotor turn. This rotor uses a magnetic field to change electrical energy into mechanical energy. Making motion. The rotor spins halfway, a commutator takes over. It reverses the direction of the current. This keeps the rotor turning in the same direction instead of changing directions halfway. As the rotor spins, it turns something called the axle. The axle is often attached to something that spins, such as the blades of a blender or a fan. The axle causes the device to spin. Now the motion of the motor has changed to the spinning motion of the device. Battery, rotor, axle. Generators and electricity. You know now how a motor changes electrical You now know how a motor changes electrical energy into mechanical energy. But can machines change mechanical energy into electrical energy? Yes. A generator is a machine that turns a coil of wire around powerful magnets, changing motion into electrical energy. Generators give us the energy we need to run our cities. When water flows through a dam, it provides the motion needed to run the dam's generator. When turning the blades of the wind on a turbine also helps create electricity. Hoover Dam's generator, right, uses magnets to change the motion of water into electrical energy. Wind farms are made up of rows and rows of turbines. A turbine is turned by moving wind or water. There are wind farms in different parts of California. One of the biggest is east of Los Angeles near Palm Springs. Another large one is near Altamont Pass outside of San Francisco. The blades of wind turbines can be 60 meters long. California has over 13,000 wind turbines. Together, they are capable of producing enough energy to light San Francisco. Wind flowing through this mountain pass gets captured by wind turbines.